All right, so let's talk about confidence intervals, and let's talk about the idea of how they're derived, first of all. And let me start by just looking at something in the book here with you. It's a guide, you might say, for constructing confidence intervals. It's in chapter 7. Well, first there's the definition of a confidence interval. A 100 times 1 minus alpha percent confidence interval. The most common thing is to pick alpha to be 0.05. So that 1 minus alpha is 0.95, and we're talking about a 95% confidence interval, is a random interval written as a closed interval. It could be written as an open interval. It's not really a big deal. L1 to L2. L1 and L2, the left and right endpoints, are random variables. I don't know if you've ever thought about that before, but the endpoints of a confidence interval are random variables. Actually, in my mind, it'd be better to call them L and R for left and right. Left one, left two, no. So it's still a left endpoint and a right endpoint, such that this property holds the probability that your parameter value is between these endpoints is 1 minus alpha. And again, in the most common case, that would be 0.95, regardless of the value of theta, which you don't know, right? In practical situations, you almost never know what theta is unless you're doing simulation and really trust your simulation. You never know the exact value of theta. But even in this definition, you can see there's freedom in how we might construct L1 and L2. It's certainly not specified exactly how to construct them. Okay, we really do have some freedom here. They also put the dot above the equal sign. I don't know if you noticed that. That really means approximately equal to. We're not after exact probabilities necessarily. That would be ideal perhaps, but not necessarily. This is going to be an applied thing. It's an approximation. And it's this line here, this sentence, that I'm after here. To construct a 100 times 1 minus alpha percent confidence interval for a parameter theta, like a population mean, most commonly theta is mu, we shall find a random variable whose expression involves theta, or mu if we're talking about a mean, and whose probability distribution is known, at least approximately. Okay, so let's go ahead and think about it in the common case of chapter 7, where we are talking about a population mean. We're trying to estimate a population mean. And for the sake of making things simpler, in chapter 7, we assume that the population variance is known. Construct a 100 times 1 minus alpha percent confidence interval. So I'm not writing down the formula for it. I'm trying to think about the construction of it to estimate mu, a population mean, when sigma squared, the population variance, is known, which of course also means sigma, the population standard deviation, is known. Okay, construct, not writing down the formula right away. What's the idea behind the construction? And the last sentence that I just read, we want a random variable whose expression involves mu in this case, and whose probability distribution is known at least approximately. In this context, in the context of the confidence interval from chapter 7, we are going to assume we are sampling from a normal population. X bar is known by this cornerstone theorem, we called it, to be normally distributed with mean, mu, and variance sigma squared over n. And therefore, if I standardize it by subtracting mu, by subtracting the parameter I want to estimate, and dividing by the square root of that, the standard deviation, we know that's a z, a standard normal. We have fulfilled this goal. If it's a normal population that I'm sampling from, I know by that cornerstone theorem, what we've called the cornerstone theorem, that X bar, the sample mean, is in fact, if it's a normal population, normally distributed with a mean of mu and a variance of sigma squared over n. And that's going to mean if I standardize, X bar minus mu divided by the standard deviation, not the variance, square root of the variance, sigma over square root of n, that's going to be standard normal, n0, 1. And there we have it. There we have a statistic, an expression involving the unknown parameter mu, whose distribution is known. And I'd now like to construct L1 and L2 so that this kind of probability is satisfied. The standard way to do it, thinking geometrically here, is to draw a normal curve. In fact, this is supposed to be the standard normal curve here. So this is 0. 1 would be about here. -1 would be about here. I'm drawing the inflection points there of the curve. This is standard normal curve. The standard way to approach this, given alpha, i.e., given 100 times 1 minus alpha %, is to do it symmetrically. Pick, I'm not going to draw them, but pick numbers on the horizontal axis that are symmetric about 0, meaning they are opposites of each other, like 1.96 and -1.96 are our favorite ones to use, in such a way that the area under the curve between those two numbers is 1 minus alpha. Therefore, the area to the right of the rightmost one plus the area to the left of the leftmost one is alpha. And each individual area is alpha over 2. And then use that picture to help you solve for L1 and L2 and get the usual formula. X bar plus or minus z sub alpha over 2. Can you imagine in your mind? Times sigma over square root of n. I'm not going to write it down. Let's do something different though. We have freedom. We still want this to be true. We want this probability to be 1 minus alpha, but I don't have to pick two numbers that are symmetric about 0. I could pick them to be asymmetric. Maybe like this. Maybe this area is 1 minus alpha. And I purposely picked it to not look symmetric. Right? That number over here is further from 0 than this number is. If I do that, then the sum of these two areas still has to be alpha. Sum of areas equals alpha, but I don't have to pick them symmetrically. Those individual areas don't have to be alpha over 2. You're wondering, why are we doing this? Okay. One thing, there's a conceptual emphasis that I do have freedom. Maybe picking an interval symmetric is not the best thing to do. Maybe. Or maybe there's going to be a homework problem that I'll assign for next Tuesday. Maybe we only want to even just pick one interval. Maybe we want to pick just, or one point. Maybe we want to pick one point, like say our right endpoint, say, where the entire area to the left, going forever to the left, is 1 minus alpha. And the area to the right of that one is alpha, not alpha over 2. Maybe we will even want to do that. That could have some application. And the homework problem I'll assign, they hint that it does have application. But here I'm even saying you could pick a non-symmetric one. And just to be specific, let's pick some specific areas here involving alpha that add up to alpha. I'm going to pick, how about this area to be alpha over 5 and this area to be maybe 4 alpha over 5. just to do something strange. Let's say area equals alpha over 5, just to pick something specific, if I know alpha. But if I do pick that to be alpha over 5, that's going to imply that this area has to be 4 alpha over 5, because those two areas have to add to alpha. Which, if I do that, would make this number right there z sub alpha over 5, and would make this number over here not negative z sub alpha over 5, not technically z sub 4 alpha over 5, but instead z sub 1 minus 4 alpha over 5. Yeah. But that's what it would be about our standard labeling. Just so the notation's not so nasty, let me give these alternative names. Let's call this capital A and let's call this capital B, just to make the notation a little simpler. Just to make the notation a little simpler, if you want to write a note to yourself. I'm after this probability statement. I should start with a different probability statement. I'm trying to work toward that. What probability statement should I start with? I want the probability that this thing right there, I want to choose A and B. Well, I know what A and B are. I essentially want to figure out what L1 and L2 are, based on the fact that I know I want the probability that this thing is between A and B to be 1 minus alpha. And again, in our typical situation, if alpha is 0.05, that'd be 0.95. The goal here now is to do some algebra to isolate mu in the middle, just like theta is isolated in the middle there. And I'll have an L1 and an L2 that will not be the usual formulas. That's the goal. Before I do that, remember when we're talking probability with confidence intervals, it's always before the fact. Technically speaking, once you've computed a confidence interval, there's no randomness in the left. It's not an accurate thing to say the probability that the parameters in the interval is 1 minus alpha. It's kind of a distinction without a difference. If somebody did know the parameter value, it still might affect your betting odds. So it, in my mind, doesn't hurt to think of it as a probability, but if you want to be technical about it, all the randomness is before the fact, before we do any sampling. So the probability statement like this is only accurate before you actually sample. All right, so let's do some algebra now. I'm trying to isolate mu. I guess I should first maybe multiply everything by sigma over square root of n. No problem with there, right? The inequalities don't change direction because sigma over square root of n is definitely positive. I'm trying to isolate mu. Okay, I can isolate negative mu by subtracting x bar from everything. That isolates negative mu in the middle. But to isolate mu, then I need to multiply everything by -1, which changes the direction of the inequalities. Multiply everything by -1. That gets mu isolated. And is technically a fine thing to write, a fine final answer, but it's not written in the way that we usually write intervals, right? Usually you put the smaller number on the left and the bigger number on the right. By the way, for future teachers, anybody in math ed? Okay, one person. Okay, for future teachers, and even if you're not going to be a teacher, it's astonishing how much difficulty even college students in statistical analysis, business stats have with inequalities. They just can't get the direction right. You'd think it would be a 50-50 thing. Like if they don't know the direction the inequality goes, maybe if you graded statistical analysis, you know this. They don't know the direction the inequality goes. They guess one way or the other. It's like they guess wrong more than half the time, right? So, this is greater than or equal to that, which means this is less than or equal to that, which means that's to the left on a number line. If you've graded statistical analysis, they have trouble with that. Anyway, if I want to switch this around with less than signs, I got to switch around the position of these things. And there we have it. There's L1 and there's L2, but wait a minute. They both have minus signs. Can that be right? That one is in particular. How can there be a minus sign there? Did I do something wrong? No, I didn't do something wrong, actually. A is negative. At least if I assume alpha is bigger than smaller than 0.5. So 1 minus alpha is bigger than 0.5. A is negative. So I'm really adding a positive quantity there because I'm subtracting a negative times a positive. And in particular, if you want to plug in what A and B are, B was, for our example, alpha over 5. Oops, that's supposed to be an N there. And A was Z sub 1 minus 4 alpha over 5. This is for our example. I could have done a different example. And if you really still don't like the minus sign there on the right, you could convert it to a plus sign by using symmetry. Z sub 1 minus 4 alpha over 5 is the opposite of another number that would be right about here, say. That would be Z sub 4 alpha over 5. It's the opposite, negative Z of 1 minus 4 alpha over 5. Maybe I should have multiplied both sides of that by -1 there. That's an alpha there if you can't quite tell. So yeah, I could replace minus Z sub 1 minus 4 alpha over 5 times sigma over square root of n with plus Z sub 4 alpha over 5 times sigma over square root of n. Again, I'm assuming in everything here, alpha is less than 0.5. 1 minus alpha is greater than 0.5. Just in the usual case, that would be what you would do. You would be pretty weird to pick an alpha bigger than 0.5. I mean, usually it's less than 0.1 for that matter. So there we have it. This would be L1 and L2 for our example. And now if you want to be even more specific, we could put particular numbers in here. We could pick alpha to be 0.05, for example, the most common thing to use. If alpha is 0.05, that'll mean alpha over 5 is 0.01. And z sub alpha over 5 will be z sub 0.01. Oh, forgetting what that one is. It's not the, well, let's just compute it. Use inv norm. Area 0.99. About 2.326. You're a little more used to with 99% confidence intervals having a 0.995 there. Alpha over 2 would be 0.005. You're a little more used to this number, 2.576, when you do 99% confidence intervals. But this would be, well, I'm doing a 95% confidence interval here, because alpha is 0.05. 100 times 1 minus alpha percent is 95% for this example. But it's a non-symmetric one, so I get alpha over to 5 to be that, and then I also need to compute 4 alpha over 5, 0.04, z sub, well, z sub 1 minus, okay, let's do the other one. Z sub 4 alpha over 5 is going to be z sub 0.04. Plug in a 0.96 here. And we get about 1.751. So the interval in this kind of context not specifying x bar, sigma, or n would look like this x bar minus z sub alpha over 5, that's the 2.326 times sigma over square root of n, comma x bar plus z sub 4 alpha over 5, that's the 1.751 times sigma over square root of n. And then yes, if you had particular values of x bar, sigma, and n, you could plug them in. Something a little confusing here, perhaps, is that this interval, if you draw it, well, it's not centered at x bar, but it's longer to the left than it is to the right. Wait, how'd that happen? Isn't this point, this z value, further from 0 than this one is? Shouldn't it have been the other way around? Well, no, this is correct. That's the way the algebra works out for one thing, but intuitively, you might imagine it's more likely, since this is longer than this is, you might imagine it's more likely that mu might be over here somewhere, the true value of mu. And therefore, it's more likely that the sampling distribution of x bar is going to be more centered over there. And if it is truly centered over there, if mu is right there, say, then this point is further from mu than this point is, which more matches this point being further from 0 than this point is. Okay, so that the algebra, there's no mistakes in the algebra does lead to this, and intuitively, this is how you might make sense out of the fact that this is bigger than this. Okay, it's not symmetric about x bar. All right, so again, the point here is we have freedom in how we want to do confidence intervals, and sometimes it might be useful. I'm not saying this particular approach is useful to use alpha over 5 and 4 alpha over 5. I'm not saying that has any practical benefit. But there are other ones, like a problem all sign, that could conceivably have a practical interpretation.